Okay, today's lecture is about queues. Well, we all know what queues are. We've all been in queues. We all waited in line for queues, and we know that you enter a queue from the back, and then you work your way to the front. And when you get to the front, then you get served. And if anybody tries to go in from the side, then say, "Hey, hey, hey! No cutting, no cutting!" Right? So it means that a queue is a first in, first out. So the first thing you put in is the first thing that comes out. So a queue is very familiar thing. We've all lined up to buy movie tickets and so on. Okay? So this is very natural. But even in computers, we have a lot of users for queues. For example, you have one printer and you send a lot of documents to it, so you send documents faster than they can print. Those documents go in the print queue. And you can also use it to do modeling of the real world, like looking at how long wait time is in an application. Okay, so what are the abstract data type operations on a queue? Well, you need to be able to create the queue. Then when you're done with the queue, you need to be able to destroy the queue. You need to be able to tell, is this queue empty or not? To add things to the queue, and then to say, okay, let's process the first thing in line in the queue, and also just to say, oh, what is the first thing in line in the queue without actually removing it from the queue. So we look at the operations. You've got is empty, boolean queue. So I say, okay, is this thing empty or not, true or false? And then enqueue, we give it an item to put in the queue, and if you can't put it in, then it throws a queue exception. Dequeue is to say, okay, remove the first thing from the queue, and if it can't, maybe because the queue is empty, then throw a queue exception. Dequeue with giving me the thing that is being removed, and also just checking the thing that is in the front without removing it. So here's an example. We have a queue, we create the queue, and then we enter the first thing in the queue, a 5, and then we enter the second thing in the queue, which is a 2, enter the third thing in the queue, which is 7, and then we say, okay, what is at the beginning of the queue, and it returns 5. Then you say, okay, let's remove that thing, so now you're left with 2 and 7, and then let's remove the next thing, and you've got 7 left. So this is an example of a queue. So a queue then can give you things in the order that they went in. So for example, you have this loop. While you're not end of line, I enter things in the queue, then later on when I try and read things from the queue, then it'll be in the same order. So here is an example pseudocode. We have a queue, dequeue character, and then we're saying, okay, while it is not done, I go and get n equals 10 times n plus integer that the character represents, and then you check, is it empty or not, and then you dequeue the thing, else you're done, so it falls out of the loop. So you keep doing it while the character is a digit. So for example, then if I n equals 10 plus 0 plus 2 is 2, then n equals 10 times 2, sorry, not plus, it's 10 times 0 plus 2 equals 2, and then n equals 10 times 2 plus 4 equals 24, and then n equals 10 times 24 plus 7 is 247. So this is an example of, we are reading in the character 247, right? And then we make it into figuring out the number 247. So we can use this to read a string of characters the same as it is from right to left. Remember, we used a stack last time, but now we can use a stack together with a queue. The stack reverses the order of occurrences, while the queue preserves the order of occurrences. So a non-recursive recognition for palindromes, you can traverse the string from left to right, and you keep putting it into a queue and a stack. And then after that, you dequeue and destack, means pop, you dequeue from the queue and you pop from the top of the stack and compare each character. Then you'll see if it is a palindrome. So here example, we push A, B, C, B, D onto the queue and onto the stack at the same time. Then when we pop off, you see that when you pop off, you see that the A pops off, right? And then D pops off. Oh, it is not the same, right? But if it was same, let's say it was like HANNAH, then you see H and H there, and then A and A, and so on. So this is how you can then check to see if it's a palindrome. So how do we implement it? Well, you can implement it as an array based, or you can use it as a linked list. So a linked list with two external references to the front and the back, because last time, remember, we did the stack, we only need a reference to the front because we only added to the front and pop from the front. But with a queue, you want to add to the back and pop from the front, or alternatively add from the front and pop from the back. So that is why we need a reference to the front and a reference to the back. Another way is to have a circular linked list with one external reference. So you have the reference to the back, and then you just join in a circle. So here's a pointer-based implementation that is linear. So you have the front pointer here, and you have the back pointer here. So you either add here and remove from here, or you add here and you remove from here. With a circular linked list, you don't need a front pointer because you can just go around. So I can add here and remove from here. You can use the next link to find. So here's an example. Inserting an item into a non-empty queue. So I'm going to add 3. So I'm going to go from the back pointer. So we have new pointer, arrow next equals null, right? So new pointer, arrow next equals null. And then back pointer, arrow next equals new pointer. So back pointer, arrow next, which is this guy here, is now going to point to the new pointer. Same place as the new pointer, right? Then back pointer equals new pointer. So now we move back pointer from pointing at a 7 to pointing at a 3. So now we've added to the back of the queue. Inserting an item into an empty queue. So if you haven't got anything yet, the front pointer and back pointer are null. So before insertion, you have nothing there and the new pointer to the new node, right? So front pointer equals new pointer. So front pointer, instead of being pointing at null, is now pointing at the new pointer. Back pointer equals new pointer. So back pointer, instead of pointing at null, is now pointing at the new pointer. So now this is the node. There's one node there. It's a queue with one person in there, or one number, or one item. So deleting an item from a queue with more than one item. See, first you have to put a temp pointer equals front pointer. So original front pointer is pointing at 2, right? So with temp pointer is now also pointing at 2. Then front pointer equals front pointer arrow next. So front pointer was here, equals front pointer arrow next. Front pointer arrow next is this guy pointing at 4. So now front pointer is also pointing at 4 instead of pointing at 2. Then temp pointer arrow next equals null. Actually, like I said, that's not necessary because next thing we're going to do is delete temp pointer. So this will go away. So then front pointer goes to 4, 1, 7. So here is the code for implementing it. Okay. So as usual, we have this defines to check to see if the .h file has been included already, and we're using namespace standard. Okay, so the queue exception is that there's some problem, right? So we make a queue exception to throw the queue exception, and that's just for when there is a problem. Okay, now for the main queue p.h. So we include queue exception, and let's say we're going to have a queue type string, and then we have the class queue public. So we've got the default constructor, because when we are first making a queue, we don't really need to do anything. It just makes the queue. But we do have to make a copy constructor because the queue is going to link. So we're going to have to do that, and also a destructor. So is empty constant, right? Is this saying that is it empty or not? Return true if it's empty, and false if it's not empty. And to enqueue, you have to give it something to enqueue, and it throws queue exception. And to dequeue, you have to throw queue exception, because if it's empty, then you cannot dequeue. And dequeue and give me the thing, okay? And then get the front of the queue without dequeuing, throw queue exception, because if there's nothing there, then it can't give you the thing. And here's the queue node. We've got a queue item, type, and the item, and then the queue node, which is next. So that's a standard linked list, right? But now we got two pointers. We got queue node back pointer and queue node front pointer. So how do we implement? Constructor is nothing to do, because when you make it, it's just a box with all the things, meaning these things here, queue node. So you got your queue node pointer, that's all that's there. So there's nothing to construct. It's just going to be make sure that they're both null. That's all. Okay. Then for copy constructor, if the queue is not empty, then we need to go down the list. You have a pointer to the front and to the original and the head, and you copy it one after another, and then you copy the front pointer to the back pointer. Okay. Then you have to go to the next, and new current next, make a new queue node, and new current to next, and new current item equals origin current item, and new current next to null, and back pointer. So obviously this is not easy to follow unless you draw the picture. Okay, but remember from our stack example, this is exactly the same, except now we've got another pointer, the back pointer, to copy. Okay, so I suggest that to really understand this, you get a piece of paper out and follow line by line and draw the boxes. And if you don't understand, do ask me in the next class. Okay, so the destructor, just like in the stack destructor, while not empty dequeue. Okay, so in the stack destructor we said not while not empty pop, so this is while not empty dequeue. It's the same idea. Keep removing until until the queue is empty. So queue empty means that if back pointer is null, so once we have removed everything, back pointer will be null. So that's how we tell if it's empty. And enqueue, so we have to make a new node, and then a new pointer item, copy to the item, and new pointer next equals null. So if it's empty, front pointer equals new pointer, else back pointer next equals new pointer, and back pointer equals new pointer. And then if I couldn't allocate the memory, then you throw queue exception. So that will rarely happen unless your PC completely runs out of memory, right? So, and to dequeue, if it's empty, of course you can't dequeue, so you throw queue exception. Otherwise, you have to point the pointer to the front pointer, and if it is the same as the back pointer, this means that it is the very last node, so then you just null both pointers. But if it's not the very last node, you have to connect the front pointer to the next, just like in the picture we saw earlier. And then 10 pointer next equals null, and then delete 10 pointer, and 10 pointer equals null. Like as I said, all this making this null is not really necessary, because you're going to delete the thing in the first right after that. Okay, so then queue dequeue is check again if it's empty. So this is exactly the same as before, except that you don't have to save the item. Okay, so get front is just if it's not empty, then we just give you the front item. So that's how we do this. So here is the program to just test it. We enqueue Mehdi, Muhammad, and Bala, and John, and Sim, and then uh, DQ, DQ, DQ to get it. So you can try this code. It's in the MMLS. You just download it and you can try it out. Okay, so that was the linked list implementation. Okay, so the next thing is then the array-based implementation. So in a implementation with array, then you are actually making an array, and you have to remember where is the front and where is the back, and it's going to loop around until you get to the back there, right? You're going to go front, back, and as you push and pop, because you don't want to have to copy. So you're actually moving the front and back until you hit the end, then you have to loop around to the front again. So this means that we are doing this circular array, okay? So you don't have this problem of drifting. Now you cannot use front and back to distinguish between queue full and queue empty, because then the front may be after the back because of looping around. So here is what happens. The front passes back when the queue becomes empty. See, when you go, you delete, and then the front will go past the back. The back catches up to the front when the full queue becomes full. See, you fill, and the back catches up to the front. So that's how you know whether it is empty or full. So to detect queue full and queue empty conditions, we have to make some checks, okay? You need to keep a count of the queue items, and then to initialize the queue, set front to 0 and back to max queue minus 1 and count to 0. Then you insert into the queue by saying back equals back plus 1, okay? And then you mod max queue. So mod is when you go to the end, then you go back to 0. So like if max queue is 100, then when you go 0 to 99, then 99 becomes 0 again instead of going to 100, for example. So here you have item back equals new item, and you add 1 to count. And then you delete from a queue. You take the content equals item front, and then front equals front plus 1, and then mod max queue again, and you subtract 1 from the count. So the count then helps you know whether you are empty or full. See, because the same situation happens with the front and back. So this is how you do the array-based implementation, and I strongly suggest that you look at this code here that is included in the zip file I'm uploading to MMLS, and then you will have to draw pictures to see how it did. Okay, remember how I did it in class for the stack? Now you have to do it for the queue to understand how to do it. So there are other ways to deal with this back front problem when to tell whether it's the queue is full or empty. One way is to have this flag that you will use to distinguish between full and empty conditions instead of keeping count. And another way is you declare this max queue plus 1 locations. So you make one extra location, but you only use max queue of them for the queue items. So if you do that, then you can tell between empty and full. So the front of the queue is at position 1 of the list. The back of the queue is at the end of the list, okay? So position in the list. So this is how you can tell. And then you can also implement the queue using the ADT list by using insert at the get length plus 1, okay, for the end queue, and then remove from the front. Now the problem with that, of course, is that you are basically having to search through the list if it's a linked list, and you're basically having to do a lot of copies if it is an array-based list. So in this particular case, ADT, just using the straight ADT list is quite inefficient. The implementation, of course, is very simple, and you can look at these files to determine the implementation. And if we look at the different types of implementation, you've got the fixed size versus dynamic size. So a statically allocated array-based implementation means that you got an array, the array has a particular size. When you fill up the array, it's full. So the enqueue operation will go, uh-oh, cannot add one, so then you have to throw an exception. Whereas a dynamically allocated array-based implementation or pointer-based implementation says that, well, there's no size restriction as long as you've got enough memory, you can make it grow. Okay. Now, dynamically allocated array-based means that you have to reallocate and copy when the array is full. Okay. Whereas if you link list, you're just adding lists, like adding nodes. So, pointer-based implementation versus one that uses ADT. See, the pointer-based implementation is way more efficient because you don't have to keep searching to the end of the queue to find the place to add. You just keep track of the end of the queue using that tail pointer. The ADT approach, of course, is much easier to write because we already have the ADT list. And so it saves programming time, but it costs you in running time. So, if you have, these are the position-oriented ADTs. You've got the list, which we covered in week 1 and week 2. And then stack, which we covered last week, and then queue. So in stacks and queues, you only can access the ends of the stack or the queue. In the case of the stack, the end is the top end, and in the queue is the head end. And whereas in a list you can access all the positions, but of course you may get a performance hit doing that. So stacks and queues are actually very similar. Okay, you have the create stack and the create queue. They're very similar, right? The create queue just has an extra pointer, and the stack is empty, and queue is empty. It's very similar also. And the push is very similar to the enqueue, and the pop is very similar to dequeue, and the get top and the get front are very similar. The main difference is in the stack, you push and pop from the same end. In the queue, you enqueue and dequeue from the opposite ends. Okay, you either enqueue from the front and dequeue from the back, or you enqueue from the back and dequeue from the front. So either way will work. And the ADT list operations, generalized stack and queue operations, so you get length, insert, remove, retrieve. They are general. They can jump all over the place, but of course, if you're using a linked list queue, when you try and jump to somewhere else, it takes more time. If you're doing an array-based list, then when you try and insert and delete, it takes more time. So what is another thing we can use queues for? Well, we can simulate the behavior of both natural and human-made systems, because, like, for example, you're trying to generate statistics and then summarize the performance of an existing system, or try and predict, oh, what is the system going to look like? Because, you know, sometimes you can't do it in real life. For example, oh, I'm going to design this big system and it'll cost a lot of money to design, but I don't know what algorithm to use. So if I use a simulation in a computer to refine my algorithm before I build the system, then I could save a lot of money. Okay, so, money, time, effort, all sorts of things. So the simulation is a way to do that. So for example, if you're trying to simulate the behavior of a bank, we could say, okay, you have the teller here and then the person queuing up and how long it takes for them to queue up and get their work done. So that is example of a simulation using a queue. Okay, so that is today's lecture. So remember, you can watch this again and again, and please try out the code. Draw the boxes with the arrows and all that to understand the code, and we will be having a short quiz in the next time we meet to make sure that you have watched this and understood everything. and we will do the tutorial next time. Okay, that's it. Bye.